All right, for the final part of the pre-lecture, we're going to talk about cost functions. But to do that, we need to start with introducing the learning diagram. So this learning diagram is the idea that we are going to put all of the components of learning into a single space for you to understand. We have an unknown target function on the left-hand side, right? It's basically some mapping from some data values to the space of possible output values, okay? And when given a target function, we're going to use a learning algorithm, script A, okay, a particular algorithm chosen from a set of algorithms, okay, and use that algorithm to derive our final hypothesis, RH, right? So the H is sometimes parameterized by a theta. We saw that in naive Bayes. In some cases, like KNN, it's not parameterized at all, okay? And this is going to be hopefully the best possible H that we can pick from the set of hypotheses that's going to be closest to our actual target function. So we can make it a little more exact, right? We can say that actually our target function, we don't get to see. We only get to see it through the lens of particular data values, okay? Which we saw in the idea of concept learning as well, right? So we're going to get a set of training examples. These are going to be index 1 through M in our lectures, okay? So in this case, it might be, we're trying to figure out credit card approvals or credit approvals, and we have historical records of what we approved and who we rejected. And like I alluded to earlier, we often have a hypothesis set that we're going to pick from. And we're going to say that our training examples actually come from data, right? So the data also sometimes has a likelihood, right? So this we can consider our marginal in the case of naive Bayes. How likely is a particular data instance from the set of all possible data? With this, let's now introduce the idea of a cost function, because this is crucial. We want to be able to pick from different parameterizations of our hypothesis. So to consider which one is better, we have to be clear about when an approximation of f is good. Okay, so we're going to parameterize that or measure that by a cost function. We're going to use the symbol J. Okay, you'll also see it in many lectures as L standing for loss. Okay, here we use J for the Jacobian matrix, but you don't have to know that. Just think of the symbol J. Okay, and it's going to take as input both of these pieces of information. So we're going to calculate some type of, again, distance value. How close are we to the actual target function given the current set of parameters for my hypothesis? Okay, and to do this, we're going to actually normally decompose it into a point-wise definition. And for the scope of all of our lectures in machine learning for this introductory course, this will be the case, all right? Which means instead of thinking of this large J target function, cost function rather, we're going to think about a cost or a loss for an individual instance, okay? A particular data instance, X, and the actual value of that through the target function. Okay, so we've seen some examples. We've seen squared error, okay, which penalizes distances, okay, as well as binary error, right? This is the case for all of the categorical things that we've gone through in this lecture. Squared error, we're going to see a little bit more when we get to linear classification and regression next week, okay? So I've already answered this question, right? Which type of error or cost are we going to determine for classification? It's almost always going to be some type of binary error. Okay, I would just say a little bit more, which is that to say that these two square brackets mean a conditional statement. So here it means if the hypothesis is not equal to the actual value, then this will output a 1. So whatever is in this conditional statement, if it's true, we'll output a 1 and 0 otherwise. Okay? So from a point-wise cost to an overall cost, it's just going to be an average, okay? So we're going to take all of the points, sum them together, their individual costs, and then divide through. So when we think of the training cost, that's very simple, right? It's just going to be aggregating over all of the data instances 1 through m, calculating the cost, the difference between when we got the classification right, which would be 0, and when we got the classification wrong, which is 1, the case of classification, and that will be our training error. For the test cost, we actually don't know what our test instances is because we don't know the actual value, so we're just going to have to use the expected value, right? So given an expected x, okay, again, you might think that certain data instances are more likely to encounter than others, which would influence this. For any expected x, we want to know what its value of the j would be, and then when we sum those together, then we have our expected value for our test instance, and then our expectation over the entire data set would give us our test cost. So when we add this learning diagram to this and we incorporate the cost function, it comes in here, right? So we are trying to decide for a particular thing, a particular data instance, whether we get the right answer. Okay, so given that information, let's talk about cost functions in a little bit more detail. Okay, now it's often the case that even though we can calculate costs, we can use some human understanding of the problem to better dictate what we should be doing. Okay, so in particular, when we're deciding whether certain types of mistakes are more valuable to learn from than others, we can permute the cost function effectively. So let's take this instance about whether we're sick or not. Okay, so we have two types of costs: false positives, which means that instead of saying that we are sick, okay, our classifier actually determines that we're sick, okay, it's a +1, but we're actually well, so this is a false positive. Or we can have a false negative or reject, okay, false rejection, which means that we're actually sick, okay, but the classifier thought we were well, okay, so that's a false negative, okay? And here the labels are a little bit arbitrary. It depends on what we are meaning by positive or negative values. Here we've chosen sick to be a positive value, okay? So we can think about how should we penalize each type. Now in the original formulation where we saw on the last slide, both of these cases over here, in the false positive and the false negative, they were both cases where they're not equal to the correct classification, so they're given a cost of 1. But we might think that one of these cases is worse than another. Okay, so let's take a look at this problem again, but think about it from the lens of being at your final exam before your graduation. And you're feeling not so great, so you go to the health center and they tell you a diagnosis. Well, are you sick or not? Well, if you got a false negative, right, and we say you're actually well, okay, and you take the test, but you're actually not doing that well, okay, you're pretty sick, you don't do so well on your test, but you at least graduate on time. You don't get a great grade, maybe your grades drop a little bit. The other possibility is you actually have a cost where you have a false positive, okay, which means you're actually well, you are ready to take the exam, but actually you were declared sick and not allowed to go, okay? So you have to take the exam next year, you might have to pay tuition fees for another semester or two, and that's expensive. So we might say, well, in this case, we would say these two different costs have different values. One could be that the false positive costs a lot more for us. We don't want to pay so much money to our school. And the other case would be less costly, okay? But let's say you're in the current COVID-19 pandemic, right? And we ask yourself, are you sick? Okay? So in this case, we have the cases flipped, right? If you're actually sick, okay, you're actually sick, okay, and we actually say that you're well and you test negative for COVID-19, but you actually have it, okay, then there's a huge cost because you could go spread the virus around and get other people contaminated or sick. right? So the false positive is a bit of a hassle, right? You have to serve your stay-at-home notice, and you can't go take the test, etc. But at least you don't get a lot of other people sick. So here we would say the false negative is not so costly. The false negative is highly costly, but the false positive is not very costly. Okay, so you can see, even though they're both cases of misclassification, depending on our interpretation of the cost for the type of misclassification, that could also inform how we structure our cost function, right? If we are very averse to this case here of false negatives, we can tune our learner to accept more cases where there are false positives at the cost of false negatives so that we can minimize false negatives. So the moral of this story is that what you measure and how you measure it matters. Where possible, we should use cost functions that fit the task as specified by the user. But sometimes this is impossible. For example, if we don't have access to the original data source, or if we only have the data but not any access to the people who collected it, or we don't know what the problem represents, then we have to use something else. We can use things like plausible measures, which we'll see later about squared error, the idea that distances from the actual value that are far away are considered worse, so we want to penalize those more. We're going to see later on in tutorial this equals some type of Gaussian noise, okay? Or we can also use convenient measures, things that are easily and mathematically simple to calculate, okay? So these can be things that are going to help us make our learner converge better. Either they have closed form solutions or they admit the possibility of optimization that's very simple. The sweet spot for us is in the case where we have both plausible and convenient measures used together. We'll see how that works. In fact, our squared error measure that we use often for things like regression is actually one of these cases. So in summary, when we insert the cost function into our learning diagram, we're going to have to find a place for it here. We have the learning algorithm and the final hypothesis, so the cost function has to deal with measuring how close we can push our learning algorithm to the actual target function, right? And so I'd like you to think about where that goes. You can stop the video for a second or two, think about it, give yourself a guess, and then continue. You can see, in fact, the cost function goes between the final hypothesis and the learning algorithm because it measures how well the learning algorithm approximates the final values of f that we have.